In this video, I will show you two experiments on the topic of reflection in mirrors. In many mirrors, you cannot see yourself from head to toe. For example, in the bathroom mirror. Being able to see your whole self in the mirror depends on the size of the mirror and the position where it's hung. In the first part, I will investigate how light rays behave when they hit a plane mirror, and then compare the angle of incidence and the angle of reflection. In the second part, I will experimentally investigate whether a figure can completely see itself in the mirror when it's hung at a certain position, and observe what physically happens. Let us start with the first part of the experiment. For it, I will need an optic lamp, a circular disc with angle division, and a mirror. On the one side of the optic lamp, the light merges conically, and on the other side, the light beam is parallelized. For the experiment, I will use this side because it doesn't spread apart and I can measure more accurately. I only need a very narrow beam of light for the experiment. Therefore, I put a slit in front of the lamp. You can imagine that this narrow beam consists of many single very thin rays of light. Therefore, I will use the term light ray instead of light beam. First, I set up the lamp. Then I place the mirror on the center of the axis of the angle division carefully and adjust to improve the position of the mirror. The lamp is positioned so that the light ray falls exactly on the center of the disc. With the mirror at the center of the axis, the light ray pointing at the center, I can easily read the angles on the disc. I turn the disc and I observe both rays are in one plane, the plane of the table. I measure the angles made by the incident ray and the reflected ray with the normal to the mirror surface. The angle of incidence called alpha is 30 degrees, and so is the angle of reflection, beta. I record all measurements in a data table. The angle of incidence and the angle of reflection are the same in our experiment, and we notice that they are in the same plane. Alpha equals beta. In physics books, one finds that this law generally applies. It is referred to as the law of reflection. For the second part, I need an optic lamp, a photograph of a figure, and a mirror. The photograph should be no more than twice the size of the mirror height. I will refer to the figure's photograph as the figure. The figure lies on the tabletop. The mirror is mounted approximately at the eye level of the figure. The mirror is fixed at an arbitrary height. Then the light source is set up, and I turn it on. For the figure to see itself completely in the mirror, it has to be able to see everything from head to toe. In order to check whether the figure can see itself completely at the height the mirror is suspended, I follow the path of light. I observe that both rays are in one plane, the plane of the table. The light from the top of the figure falls on the mirror, and then the reflected light falls into the eye of the figure. This means the figure can see the top of their hat. No matter how I move the lamp, I cannot get the light from the feet reflected so that the light shines to the eyes of the figure. Therefore, the figure cannot see itself completely in the mirror. The goal of the experiment was to interpret the observations physically. Why a figure can see something in the mirror can be explained by the behavior of light that hits the mirror. The light from the top of the hat falls in the mirror and is reflected according to the law of reflection, then shining to the eyes of the figure. The reason the figure could not see its feet is also because of the law of reflection. In the experiment, no matter how the beam was positioned, the reflection wouldn't hit the eyes of the figure. However, the height of the mirror was arbitrary, and I noticed that the upper part of the mirror is not used at all. If you place the mirror with more consideration and lower, then maybe the figure will be able to see more of itself and possibly the feet. Now carry out the experiment yourself and record several measurements. Can you confirm the law of reflection with your measurements? Think about why the mirror must be at least half the size of the figure. A low-cost version that shows how to do the experiment with everyday objects and the worksheet for the experiment can be found on our website.